So in Grasshopper, we had noticed that the main issue is with the second part of our algorithm is it's not well defined enough. And it's just like we had before, we said mirror the mouth. And it's a question of, well, we didn't appreciate that the aspect of when you have a mirror, the input needs a plane. So if we were sitting here and right now and we're saying, this is what I have, right? And really, let's draw it in another color. This is what I want, roughly speaking. Yeah, what does that mean that I need in the midterm to get this to work? I probably need a mirror plane that passes somewhere through here to get from black to green. Yes, so this is the key thing here is we already know that we're going to go from black, right, to green with an intermediate step that is needing to create from black this blue. So we go black to blue and then blue to green. And this is not necessarily the way we think. Even if we were using manual CAD, you wouldn't think necessarily, oh, I need a plane. It's just not the way it works. You work in 2D plane spaces and you don't think this way. So it's easy to miss when you're first starting out the way you need to think. There is no way that you're going to be able to not get away with doing it this way, to think about the problem and say, what is it that I need to do? So let's do the input output for how this sequence works, okay? So this sequence, what's our input? First input is this, right? What's our output? We had said that was in green. The output was this, yeah? And if I'm being a little bit like this, it's just kind of the context of that is this, right? And the first step of this is let's get down from this to a situation where I've created effectively this guy through here. And again, we've kind of gone over how you do this. We know how to get this selected in Grasshopper, and we kind of already have a few techniques at our disposal for how to more well define this picture, right? So we've talked in one situation where we said, listen, what if we just said that guy right there was X and X, sort of centered on the middle, yeah? Or what if that guy potentially, again, if he was there, what if we just said that, we have an algorithm already that sort of can create that guy, and then the centroid of that guy can be defined, and then this guy can be defined as horizontal across the page here. Yeah. So it really comes down to which one do we want to do. So those are the two options, and let's just explore those two options then and how those would look, and try and learn from our previous issues that we said. So let's take this one for example, right? So we know that the input, again, going down the rabbit hole, chasing the first principles of the problem is this, and the output is something like this, where this guy is X and this guy is X, right? The equidistance from that. How do we define that as a problem? So obviously, if the entire thing is depth is L, right? So let's just start by saying if the total distance from top to bottom of the smile itself is L, then that equals 2x, okay? So let's just kind of keep that in our mind. That's our definition that we'll go with going forward. But in that situation, again, if all we have is this, how then is the first step is, how do I go from this to L, right? How do I do that? And again, this comes back to saying, what have you been given? Well, you want to go from a curve effectively to a number, right? And a curve is not a very good thing to do for a number. What kind of algorithms can we think of that take a curve and convert it to a number? Can think of a few. Length, right? So if you used something that got the curve's length, that would give you a number. The curvature of the curve at one point on the curve, that would give you a number. Something like the radius would be a similar type of thing. But you get the point. Is there isn't a off-the-shelf type of, hey, what's the deal here? What's L in the grand scheme of things that we can think of just in English, right? So we'll have to convert the curve itself to something else here, and then that something else will give us the number that we're after. We already kind of know that. We can't look at this. We can't say that the length of the curve, let's say, which we know we can get, we've used that in previous lessons, gets us this value, which is sort of the height above, let's say, from here to here. And that's the thing now, is now we start to actually, with this line, you start to get inspired of where we're headed, is really this comes down to, let's really define this problem. And it is as if we took the entire curve and we laid it down on the ground and we said, okay, from here upwards is the axis that we measure at, and the axis, the length is the distance, let's say, from the topmost point to the bottommost point. And then if you start to think that way, you've already realized that the intermediate data that we'll need here is a point, which should come as no surprise, because before we said computational engineers do a great job at conversion of one data type to another, and it all is predicated on, if you know that a curve equals infinite points, that should be in the back of your mind all the time, because we can cherry pick these points as we need them to suit us. And in this case, we've already learned the skill, for at least one of the skills, for how to maybe cherry pick off these two, right? And then potentially be able to utilize them to do our job, right? So let's say we got these 2 points, yes? So that was step one. Step one is get top and bottom points, yeah? So this is step one here, we get those 2 points. Now step two, what do we do with those 2 points? How can we get from, again, these 2 points to the number that we want, which is L, and then L over 2 would be X, yeah? And in that situation, we'd have to say, well, what are these points, right? Because is the distance between these 2 points, is that our L? One would say no, yeah? It's the vertical distance, is the distance of those 2 parallel to the axis which we've chosen, yes? So the key here is it's a little bit of an issue of, we kind of already know that would be maybe the start point or end point, and that would be the midpoint of this arc. And so we have to start thinking about ways that we could sort of make this picture well defined for the computer. That's the whole thing, is this picture is what we want, but it's predicated on the fact that we already have this direction, yeah? So this direction is something actually we've just drawn, but we don't have actually. So actually we need to make more well defined this guy right here, because we've already had the situation where we go over to the computer and we don't have the problem well defined enough. And we've had it before in the rotation, and now we're going to have it again here. If we don't define this, we will only be able to say we have 2 points, and logically, those 2 points really don't define the vector that is this way. And if we don't have that vector, you won't be able to define really the distance that we're after, which is this distance right here. So what can we do? So first thing we can do is we can try and establish, again, understanding from first principles, establish the direction of this vector. So establish direction of the sort of height vector, right? So let's just try and see if we can establish that. And again, I would just go and I'd say it's the easiest thing to do would be to say, listen, let's take some of the tricks from our old script. Let's create this line from A to B, which are the endpoints. Let's get the midpoint. Let's get the midpoint of this curve, and let's create a line from C to D, and that line represents that vector. So we would know right then and there that that one actually is, not only is it the establishment of the direction of the height of the vector, but actually it's also the length, right? So again, I'm taking you through this. I'm doing a reasonable, I'm not doing it with a preset defined way of doing the algorithm itself. which is why I'm trying to show you the way you should think. And a lot of times you'll start off on one little tangent here and you'll start moving towards the solution. And then actually, because you're trying to solve one part of this solution, you'll actually end up on the real, more succinct solution here. So this is about learning a way of thinking and a way of problem solving. I'm not going to sit here and try and teach you how to do it the right way, quote unquote, because there is no right way. There's only the right approach, which is in this case coming from first principles and realizing that actually if we wanted to do it this way, we would need to effectively boil down, and again, chapter 1's all about this, boil down a curve, right, into a set of a number. That would be it. And actually, it's not just a number. It's actually, this was wrong. It's a curve to a vector. And if we get that curve and that curve converted to that vector, then not only is we can get this picture, because this picture is predicated on the fact that that blue line isn't drawn like this. Yes, it's drawn horizontally across. It's drawn orthogonal to this particular vector here. Now, with all of that in mind, let's go back to Grasshopper, utilize that knowledge. It's a well-defined problem on paper. We now have the clarity of how we go forward. We convert this curve into a vector, utilizing an algorithm, something like this. And then once we have that, it should be a fairly simple, straightforward process for us to be able to create that axis and mirror about the central plane.